The universe is not just expanding, it is speeding up. This fact, discovered just over 2 decades ago, overturned a fundamental assumption about cosmic fate and revealed a profound mystery at the heart of reality. We call this phenomenon cosmic acceleration, and it implies that something invisible, something we do not understand, is pushing space itself apart with ever-increasing force. By the end of this exploration, you will understand the 30 greatest puzzles surrounding this acceleration, from conflicting measurements to theories that challenge the fabric of physics. We will confront why 2 precise ways of measuring the universe's expansion disagree, and question whether the leading explanation, a mysterious dark energy, could one day tear reality apart at the seams. What does it mean to live in a cosmos that is actively and mysteriously running away from itself? This acceleration is not just a singular mystery, it is a doorway into dozens of them. And the very first, the most fundamental puzzle we must confront is a conflict in the numbers that define our universe's expansion. Astronomers call it the Hubble-tension. For nearly a century, we have known the universe is expanding. The rate of that expansion is called the Hubble constant. It is a single, crucial number that tells us how fast space is stretching at a given distance. Pin this number down, and you can calculate the age of the cosmos, understand its past, and predict its future. So, naturally, scientists have spent decades refining their measurements, using the most powerful tools available. And here is where the trouble begins. 2 of our most trusted, most precise methods for measuring this number are giving us different answers. It is as if you used 2 perfectly calibrated rulers to measure the same table, and each one gave you a different, definitive length. The first method looks back to the very dawn of time, to the afterglow of the Big Bang itself. This is the cosmic microwave background, a faint whisper of radiation that fills all of space, a snapshot of the infant universe when it was just 380,000 years old. By studying the subtle patterns in this ancient light with satellites like Planck, cosmologists can work backwards. They plug the data into our best model of cosmic evolution, which includes all the dark matter and dark energy we think is there, and it spits out a predicted expansion rate for today. This is a measurement from the beginning, forecasting the present. The second method is more direct. It measures the universe as we see it right now in our cosmic neighborhood. Astronomers use celestial mile markers called Cepheid variable stars and cataclysmic explosions known as Type 1, a supernova. Cepheids pulse at a rate directly tied to their true brightness. By measuring their pulse and how dim they appear from Earth, we can calculate their exact distance with remarkable accuracy. Supernovae are even brighter, acting as standard candles visible across vast distances. By watching how fast galaxies containing these objects are moving away from us, and knowing precisely how far away they are, we get a direct, local measurement of the Hubble constant. Both methods are monuments of human ingenuity. Both are incredibly precise, and they disagree. The early universe measurement suggests a slower, more sedate expansion rate. The local, modern measurement insists the universe is expanding faster. The gap between them is not a small statistical blip. It is a chasm with a significance of over 5 sigma, a term in science that means the chance this is a random error is less than 1 in 3.5 million. This is the Hubble tension. It is a stark warning that something in our story is wrong. Perhaps our observations contain a subtle, unaccounted for error. Or, more thrillingly, perhaps our standard model of cosmology is missing a crucial ingredient, a piece of physics that operated differently in the ancient universe than it does today. This is not just a debate about a number, it is a direct challenge to our understanding of cosmic history. This disagreement in the numbers forces us to confront the leading suspect in the case of cosmic acceleration, an entity so dominant it makes up about 68% of everything in the universe. We call it dark energy. It is the name we give to whatever is causing the expansion of space to speed up. But what is it, really? The simplest, and currently the most favored, idea comes straight from Albert Einstein's own equations. He included a term he called the cosmological constant, represented by the Greek letter lambda. He originally put it in to keep the universe static, a notion he later called his greatest blunder. But in a stunning twist of fate, modern cosmology has resurrected it. In this view, dark energy is not a substance flowing through space. It is a property of space itself. Empty vacuum, according to quantum physics, is not truly empty. It seethes with virtual particles flickering in and out of existence. This quantum activity endows every cubic centimeter of nothingness with a tiny, constant energy density. This is the cosmological constant, a uniform energy woven into the fabric of space-time that exerts a repulsive force, pushing space apart. The key to its pushing power is a bizarre quality called negative pressure. Think of it this way: if you put positive pressure into a balloon, like your breath, the balloon expands. That makes sense. Dark energy works like a negative pressure. Imagine trying to inflate a balloon by pulling outward on its rubber. That negative tension, that pull, would also cause the balloon to expand. On the cosmic scale, this negative pressure of the vacuum acts as a sort of anti-gravity, causing the universe to stretch itself apart at an ever-increasing rate. It is an elegant, simple solution, but its simplicity masks a problem of such staggering magnitude that it is often called the worst theoretical prediction in the history of physics. The cosmological constant problem. When physicists try to calculate how much energy this quantum vacuum should have based on known laws, the number they get is absurd. It is about 120 orders of magnitude too large. That is a 1 followed by 120 zeros. If that calculated value were correct, the repulsive force would have been so unimaginably powerful that it would have blown the infant universe apart instantly, preventing stars, galaxies, or us from ever forming. The fact that we exist means the observed value of dark energy is almost zero, but not quite. So why is the theoretical number so catastrophically huge, while the real, measured number is so infinitesimally small? We have no idea. It is as if we have the right name for the suspect, lambda, but the fingerprint we found at the scene is 100 trillion times smaller than the fingerprint our theory says the suspect must have. This is not a small gap in understanding. It is a yawning abyss, suggesting that something fundamental in our marriage of quantum, mechanics, and gravity is deeply, profoundly wrong. This gap between prediction and reality is so vast it defies ordinary description. To grasp the scale of the cosmological constant problem, consider a single grain of sand. The energy density that quantum field theory predicts for empty space, based on the ceaseless dance of virtual particles, would be like expecting that grain of sand to contain the mass of our entire observable universe. The actual, observed energy of dark energy, the tiny push that is accelerating the cosmos, is that grain of sand's true, minuscule weight. The prediction is not just a little off, it is wrong by a factor of 10 to the power of 120. That number is so incomprehensibly large, it has no name. If this theoretical vacuum energy were real, the repulsive force would have been so immense that the universe would have expanded to near infinite size in a fraction of a second after the Big Bang. No atoms could have formed, let alone galaxies, stars, or planets. The very fact that we are here to ponder the question means the actual value is almost perfectly balanced at nearly zero, but crucially, not exactly zero. This is the core of the problem. Why is the vacuum energy we measure so vanishingly small compared to what our best theories insist it should be? It suggests one of two terrifying possibilities. Either our understanding of quantum mechanics, which works flawlessly on the scale of atoms, is catastrophically incomplete when applied to the emptiness of space, or there exists some unknown, perfectly tuned cancellation mechanism. Perhaps an array of different quantum fields and their energies sum together in a miraculous way to almost completely cancel out, leaving behind only the faintest whisper we detect as dark energy. The fine-tuning required for this is beyond staggering. It feels unnatural. This is why the cosmological-constant-problem is not merely a puzzle. It is a screaming clue that our two great pillars of modern physics, quantum mechanics and general relativity, are fundamentally incompatible when it comes to describing the energy of nothingness. Unifying them into a theory of quantum gravity is the holy grail of physics, and solving the vacuum energy problem is the most glaring signpost on that quest. Until we can explain why empty space isn't bursting with the energy our math says it has, the true nature of dark energy will remain shrouded in mystery. But if the cosmological constant is so problematic, perhaps we have the wrong suspect entirely. The assumption baked into that simple model is that dark energy is constant, an immutable feature of empty space that has not changed one bit in 13.8 billion years. Its strength, its density, would be the same now as it was in the primordial universe, and as it will be a trillion years from now. This is a huge assumption. And it is one we can actually test. To do this, cosmologists use a simple but powerful number called the equation of state parameter, represented by the letter W. This number describes the relationship between the pressure and energy density of whatever dark energy is. For Einstein's cosmological constant, the math is very specific. W must equal exactly -1. That specific value gives us the constant, unchanging dark energy that drives acceleration at a steady rate. But what if W is not -1? What if it is something like -0.95 or -1.05? That tiny deviation would be a cosmic earthquake. It would mean dark energy is not constant at all. It would tell us that the force accelerating the universe is dynamic, that it has evolved over cosmic time, growing stronger or weaker. This hypothetical, evolving form of dark energy has a name, quintessence, named for the ancient fifth element beyond earth, air, fire, and water. Unlike the static cosmological constant, quintessence could be a field, similar to the Higgs field, that permeates space but whose energy can slowly shift and change. It could even interact with other components of the universe. So how do we measure this elusive W? We go back to our cosmic detectives, supernova. By observing type 1, a supernova at vastly different distances, we are looking back into different eras of cosmic history. A supernova that exploded 9 billion years ago shows us the universe when it was younger and denser. By comparing how much it has been dimmed and stretched by the expansion of space to one that exploded just 1 billion years ago, we can measure how the rate of acceleration has changed over time. Did it kick in with the same force throughout history, or did it ramp up slowly? Another method uses the fossilized sound waves from the early universe, called baryon-acoustic-oscillations. These left a faint, regular pattern in the distribution of galaxies, a standard ruler etched across the cosmos. By measuring the apparent size of this ruler at different epochs, we can trace the expansion history with incredible precision, searching for any subtle deviation from the prediction of a constant dark energy. The latest results from these painstaking observations are tantalizing and frustrating. They suggest that W is incredibly close to -1, consistent with a cosmological constant. But the error bars, the range of uncertainty, still leave a little room for quintessence to hide. The data does not yet scream evolution, but it whispers the possibility. This makes the question of constancy one of the most active fronts in modern cosmology. Is the accelerating force a fixed feature of the universe's stage, or is it an actor that can change its role? The answer will determine the ultimate fate of everything. That whisper of possibility from quintessence opens a door to something far more unsettling. If the equation of state parameter W is not just slightly different from -1, but is actually less than -1, we enter the realm of phantom dark energy. This is not merely a dynamic force, it is a force that grows stronger and more terrifying with time. For ordinary substances, even for the cosmological constant, the energy density dilutes as the universe expands. Picture a drop of ink in a glass of water, spreading out and becoming fainter. Phantom dark energy flips this logic on its head. As the universe stretches and grows larger, the density of this phantom energy does not decrease, it actually increases. It is as if that drop of ink, instead of fading, becomes darker and more concentrated the more water you add. This bizarre, self-amplifying property leads to a cosmic fate so violent it has earned a dramatic name, the Big Rip. In this scenario, the repulsive force of dark energy does not just accelerate the expansion of space between galaxies, it accelerates without limit. Billions of years from now, the force would become so strong that it would overcome the gravity holding our Milky Way together. Stars would be flung away from each other into the deepening void. As the end draws nearer, the phantom force would escalate. A few million years before the finale, it would rip apart our solar system, pulling planets from their orbits. Months or weeks out, Earth itself would be torn apart. In the final minutes, the force would exceed the nuclear forces binding atoms together. Every molecule, every atom, every proton and neutron in what was once the universe would be violently shredded into disconnected elementary particles, leaving behind a cold, empty, utterly featureless cosmos, where not even the structure of space and time as we know it could exist. It is a definitive and horrifying end to all structure. The critical question is, does our universe show any signs of heading toward this oblivion? The current data from supernova and cosmic microwave background measurements suggests W is incredibly close to -1, and statistically consistent with it. The error bars, those ranges of uncertainty, do slightly extend into the phantom regime, meaning we cannot yet completely rule it out, but there is no strong, definitive signal pointing to a value less than -1. For now, the Big Rip remains a hypothetical specter on the far edges of our cosmological models, a reminder of how profoundly the true nature of dark energy dictates not just the universe's expansion, but its ultimate, final act. The ultimate fate of the universe hinges on a number we cannot yet pin down, but to understand why our present moment feels so strange, we must look not just forward, but backward across the entire timeline of the cosmos. This brings us to a profound and unsettling puzzle known as the coincidence problem. For nearly the entirety of cosmic history, the universe was dominated by one ingredient or another in a lopsided, overwhelming fashion. In the first fleeting moments, radiation ruled. Then, for billions of years, dark matter held sway, its relentless gravity sculpting the cosmic web and pulling galaxies together. Throughout this vast stretch of time, dark energy, if it existed at all, was an utterly negligible whisper in the background, contributing almost nothing to the total energy budget of the universe. Then, about 5 billion years ago, something shifted. As the universe expanded and matter diluted, the density of dark matter steadily decreased. Meanwhile, if dark energy is a cosmological constant, its density remains stubbornly the same in every cubic centimeter of space. There came a point where the fading density of matter finally dropped below the constant density of dark energy. In that moment, the repulsive force of the vacuum won the cosmic tug-of-war, and the era of acceleration began. Here is the staggering coincidence. We find ourselves living in the cosmic epoch where these two titanic, yet utterly different, components are roughly comparable in strength. The energy density of dark matter and the energy density of dark energy are of the same order of magnitude. This is like walking into a room at the exact second a scale perfectly balances, with two wildly different weights momentarily in equilibrium. For the vast majority of the past and the almost infinite future, this balance does not exist. In the distant past, dark matter was 1,000,000 times more dominant. In the far future, dark energy will be 1,000,000 times more dominant, driving the universe into a lonely, diluted emptiness. We exist in a sliver of cosmic time, a window that is astronomically thin compared to the lifespan of the universe, where we can witness this transition. Why now, if dark energy is a simple constant of nature, then this is just a random accident of timing. We are cosmic latecomers who showed up for the main event. But to many scientists, that answer feels deeply unsatisfying. It reeks of a specialness, a fine-tuning that begs for a deeper explanation. Could this coincidence be a clue instead of an accident? Perhaps dark energy is not a constant, but something that evolves in relation to matter. Some theories propose a direct interaction between dark energy and dark matter, an unseen dialogue where one influences the density of the other, naturally leading to an epoch where their strengths align. Others suggest more radical ideas, like theories of a cyclical universe, where such transitions happen repeatedly. The coincidence problem forces a difficult question. Are we simply lucky to be alive during this unique, transitional era? Or is our very presence as observers somehow linked to the conditions that make observation possible? It is a puzzle that blurs the line between cosmology and philosophy, hinting that our place in the cosmos might be far less accidental than it appears. The profound strangeness of our present epoch forces us to look for clues not just around us, but in the deepest past. Could the key to today's cosmic conflict lie in the first moments after the Big Bang? This leads us to a fascinating and speculative idea known as early dark energy. The standard story says dark energy was a sleeping giant for billions of years, only awakening recently. But what if that is wrong? What if a burst of this repulsive force was also active in the universe's infancy, a fleeting echo of the acceleration we see today? Theorists propose that in the first few 100,000 years, a temporary form of dark energy could have briefly surged and then faded away. This is not the constant dark energy of today, but a transient, early phase. Its potential impact centers on a crucial ruler etched into the cosmos, the sound horizon scale. To understand this, we need to listen to the echoes of the young universe. In its first few 100,000 years, the cosmos was a hot, dense plasma, a searing fog of particles and light. Pressure waves, like sound waves, rippled through this fluid. When the universe cooled enough for atoms to form, a moment called recombination, the fog cleared, the light finally broke free, becoming the cosmic microwave background we detect today. Those frozen sound waves left a specific signature, a preferred scale imprinted in the CMB's temperature patterns and in the later clustering of galaxies. This scale, the sound horizon, is the farthest distance a sound wave could have traveled before the universe became transparent. It is a standard ruler of known physical length. Cosmologists use the apparent size of this ruler on the CMB sky to calculate fundamental properties, including the predicted expansion rate for today. Here is where early dark energy enters as a potential game-changer. If an extra dose of repulsive energy was active just before recombination, it would have given the universe a tiny, temporary speed boost in its expansion. Think of it like a brief tailwind during a marathon. That extra push would have affected how far those primordial sound waves could travel. The sound horizon ruler would have been set slightly smaller than in the standard model. This is critical. When we look at the CMB and measure the apparent size of that ruler, we then work backwards to deduce the universe's expansion history. If the actual ruler from the early universe was smaller than we thought, then to make it appear the same angular size on the sky today, the universe must have expanded less to reach its current scale. This adjustment leads to a higher predicted value for the Hubble constant today, potentially bringing it into closer alignment with the faster rate measured locally. In essence, early dark energy offers a way to tweak the starting conditions of our cosmic model, altering the calibration of our most ancient ruler to resolve the tension in modern measurements. Several models propose what this early energy could be, often linking it to scalar fields that decayed or changed phase. However, this elegant idea is not a free pass. The cosmic microwave background is an exquisitely precise dataset. Adding early dark energy changes not just the sound horizon, but also affects other subtle features, like the relative heights of the temperature fluctuation peaks. Current data from the Planck satellite and other observatories places tight constraints on these models. While some versions are still viable, the data strongly prefers the standard cosmological model without this early boost. The evidence for early dark energy is, at best, tentative and controversial, yet it remains a compelling avenue of research because it directly tackles the Hubble tension by modifying physics in the primordial universe. It asks us to consider a radical possibility that the force now tearing the cosmos apart was not silent in the beginning, but whispered once before, leaving a faint fingerprint we are only now learning how to read. The search for early dark energy pushes our models to their limits, but what if the answer requires no exotic physics at all? What if cosmic acceleration is not a fundamental force, but a grand illusion born from our own unlucky place in the cosmos? This is the radical proposition of the void model, sometimes called the Hubble bubble. Imagine our entire observable universe, the sphere of space we can see, is not a fair sample of the whole. Instead, we might be sitting in the center of a vast cosmic underdensity, a gigantic bubble where the average density of galaxies and matter is significantly lower than the true cosmic average. Outside this bubble, the universe is much denser. This is not a small local variation, but a continent-scale fluctuation hundreds of millions of light-years across. How could this create the illusion of acceleration? It all comes down to gravity. In Einstein's general relativity, the expansion rate of the universe is not a single global number. It is a local measurement that depends on the density of matter around you. Inside our hypothetical void, there is less matter pulling on space with its gravity. With weaker gravitational attraction holding it back, the space inside our bubble would expand faster than the denser universe outside. From our vantage point, looking out at galaxies, we would measure this faster local expansion. Crucially, as we look to greater distances, our line of sight eventually passes beyond the edge of our bubble and into the denser, slower expanding outer universe. The transition could create an observational signature that looks exactly like an acceleration, a change in expansion rate with distance, without any dark energy whatsoever. It would be a cosmic mirage, a trick of perspective on the grandest possible scale. This idea is powerfully appealing in its simplicity. It replaces a mysterious, dominant component of the universe with a single, albeit enormous, lumpiness in the distribution of matter we already know exists. But for this illusion to hold, the void must be nearly perfectly spherical, and we must be astonishingly close to its exact center. If we were off-center, we would see a directional bias in the expansion, a faster rate in one hemisphere of the sky and a slower rate in the other. Furthermore, the void would have to be mind-bogglingly large, perhaps 1 billion light-years in radius, to mimic the observed signal. Such a gigantic structure would itself be wildly improbable according to our standard model of cosmology, which predicts a mostly smooth universe on the largest scales. The most damning evidence against this idea, however, comes from the oldest light we can see. The cosmic microwave background is exquisitely isotropic, meaning it has the same temperature in every direction to about 1 part in 100,000. If we were in the center of a vast underdensity, the gravitational pull of the denser walls of matter surrounding our void would affect the light from the CMB as it traveled to us. The photons climbing out of the gravitational well of the dense outer universe would lose energy, appearing slightly cooler, while those falling into our void would gain energy, appearing slightly warmer. This would create a distinct, measurable temperature gradient across the sky, a hot spot in one direction and a cold spot in another. We do not see this. The CMB's near-perfect uniformity is a death knell for the idea that we occupy a special, central location in a giant bubble. The data forces us to accept a more humbling and profound truth, that on the largest scales, the universe really is homogeneous, and our observations of acceleration must reflect a genuine physical phenomenon, not a trick of our address. The void model, while a brilliant exercise in questioning assumptions, ultimately highlights just how robust and inescapable the evidence for cosmic acceleration truly is. The void model's failure reinforces a difficult truth, that the evidence for acceleration is etched into the cosmos itself, but this forces a profound question, one that strikes at the very foundation of modern physics. What if we have been misdiagnosing the symptoms entirely? The entire dark energy paradigm rests on a crucial assumption that Albert Einstein's theory of gravity, general relativity, is absolutely correct on the scale of the entire universe. This is the radical alternative, that the mystery of cosmic acceleration is not caused by an unknown substance, but by our incomplete understanding of gravity itself. This idea has a name: modified Newtonian dynamics, or MIND. Its origins lie not with the expanding universe, but with a separate cosmic puzzle, the rotation of galaxies. For decades, astronomers have observed that stars at the outer edges of spiral galaxies orbit far too quickly. According to Newton's and Einstein's laws, these stars should be flung off into intergalactic space given the visible mass of stars and gas we can see. The prevailing solution is dark matter, an invisible halo of matter providing the extra gravitational glue. Mund proposes a different fix. Instead of adding invisible matter, it subtly changes the laws of gravity at extremely low accelerations, like those experienced in the faint outskirts of galaxies. In this framework, gravity does not weaken with the square of the distance as precisely as Newton predicted when its pull becomes incredibly faint. This single modification can beautifully reproduce the observed rotation curves of hundreds of galaxies without invoking a single particle of dark matter. It is an elegant solution to one major puzzle. The ambition, however, is far greater. Could a modified theory of gravity also explain cosmic acceleration, doing away with dark energy as well? To even attempt this, scientists had to build a full relativistic version of Mund, a theory that could compete with general relativity on cosmological scales. The most prominent attempt is called tensor vector scalar gravity, or TVS. In this framework, gravity is not just the curvature of spacetime described by Einstein. It is mediated by multiple fields, including a scalar field that can vary across space and time, adding an extra layer of influence. Proponents showed that under certain conditions, this modified gravity could, in principle, produce an accelerating expansion of the universe without any dark energy. The allure is immense. A single shift in our understanding of a fundamental force could erase two of cosmology's greatest mysteries at once. But the path is fraught with monumental challenges. While simple Mund works remarkably well for individual galaxy dynamics, scaling it up to describe the entire cosmos has proven extraordinarily difficult. The relativistic versions like TVS often struggle to match the exquisite precision of the cosmic microwave background data, which the standard model of cosmology, with its dark matter and dark energy, fits with stunning accuracy. These modified gravity theories also have a hard time explaining the observed behavior of massive galaxy clusters, where the gravitational lensing of light reveals far more mass than Mund alone can account for. Furthermore, the Bullet cluster, a spectacular collision of two galaxy clusters, presents a severe blow. Observations show that the bulk of the mass, deduced from gravitational lensing, has sailed right through the collision, separated from the visible gas. This behaves exactly as expected for dark matter, a collisionless substance, but is extremely difficult for modified gravity to explain if all gravity is tied directly to the visible matter we see. Perhaps the most telling challenge is one of naturalness. Introducing a modification to gravity to explain galaxy rotations is one thing, but engineering that same modification to also precisely mimic the observed acceleration of the entire universe often feels like fitting two very different locks with a single, overly complex key. The adjustments required can appear contrived. This is not to say the pursuit is worthless, far from it. The persistent anomalies in our universe demand that we question our core assumptions. Modified gravity remains a vital counterpoint, a reminder that the dark universe of matter and energy is an inference based on the laws of gravity as we currently write them. If those laws are even slightly different on vast scales, the entire cosmic ledger changes. The ongoing tension is a testament to the scientific process, a rigorous tug of war between inventing new cosmic ingredients and rewriting the fundamental rules of the game. The battle between new ingredients and new laws of gravity is fought with equations. Among the most promising soldiers on the modified gravity front are theories that do not discard Einstein's masterpiece, but elegantly edit it. These are known as F of R gravity and scalar tensor theories. They start from a profound place, the very action principle that defines how spacetime curves in response to mass and energy. In Einstein's original formulation, this action depends linearly on a quantity called the Ricci scalar, R, which is essentially a measure of how severely spacetime is curved at a point. It is a beautifully simple foundation. F of R gravity asks a simple, radical question. What if the action depends on a more complex function of R, not just R itself? By replacing the linear term with a custom function, F of R, theorists can introduce new dynamics into the fabric of gravity itself. Imagine the force of gravity is like a spring. In Einstein's theory, it is a perfect, linear spring. Its pull proportional to how far you stretch it. F of R gravity suggests the spring might be more complex, perhaps stiffening or softening in certain regimes. On cosmic scales, this modified behavior can mimic the effects of dark energy. A carefully chosen F of R function can cause the universe's expansion to accelerate without any mysterious energy component, purely as a consequence of how gravity behaves when spacetime becomes extremely stretched and empty. The universe accelerates because, in this modified framework, gravity itself weakens in a specific way over vast distances. It is a compelling mathematical sleight of hand, replacing an unknown substance with a refined law. But the universe is a ruthless laboratory. These theories are not free parameters. They must pass every test that general relativity aces. They must correctly predict the orbit of Mercury, the bending of light around the Sun, and the precise timing of binary pulsars. Crafting an F of R function that explains cosmic acceleration while surviving these local, high-precision tests is a formidable tightrope walk. Often, to satisfy all constraints, the function must be engineered to behave almost exactly like Einstein's theory within our solar system, only deviating on the scale of the entire cosmos. This fine-tuning can feel as puzzling as the dark energy it seeks to replace. A close cousin to this idea is scalar tensor gravity. Here, the modification is more tangible. An extra field is woven into the cosmic fabric alongside spacetime. Think of it this way: in Einstein's universe, gravity is the geometry of the stage on which particles act. In scalar tensor theories, there is also a director on that stage, a scalar field that can vary from place to place and time to time, influencing how strongly gravity pulls. The most famous historical example is Brand's Dick theory, which proposed a gravitational constant that was not truly constant, but could evolve, mediated by this new scalar field. In modern versions, this dynamic scalar field can roll down a potential hill, its evolving energy acting as a driver for cosmic acceleration. It becomes quintessence, but born from gravity's own extended family rather than being an independent dark energy. The crucial power of these theories is that they make distinct, testable predictions. They alter how gravitational waves travel through the cosmos, or how the growth of cosmic structure, the clumping of galaxies over time, unfolds. In standard dark energy models, gravity is unchanged, so dark energy only affects the expansion rate, which in turn influences how easily structures can form. In many modified gravity models, the force of gravity itself is directly altered on large scales, which can suppress or enhance the growth of galaxy clusters in a measurable way. Upcoming telescopes, like the Vera-C, Rubin Observatory, and the Euclid Space Mission, are designed to map the cosmic web in unprecedented detail, precisely to catch gravity in the act. They will measure the rate of structure growth across billions of years, looking for any deviation from the predictions of general relativity with simple dark energy. A discrepancy would be a smoking gun, not for a new particle, but for a new law. The pursuit of F of R and scalar tensor theories represents a breathtaking ambition to solve the greatest cosmic mystery not by filling the universe with ghosts, but by listening more carefully to the subtle, still unknown language of spacetime itself. The ambition to rewrite gravity confronts the deepest principles of physics, principles that string theory seeks to unify. This quest leads to a startling possibility that our accelerating universe might be incompatible with the ultimate laws of nature. This is the realm of the swampland conjectures. In theoretical physics, there is a metaphorical landscape. On the high ground lies the string theory landscape, a vast but finite set of possible universes that can emerge from string theory's equations, each with its own constants and physical laws. Below it lies the swampland, an infinite set of seemingly consistent theories that are nonetheless impossible to realize in a universe that includes quantum gravity. They are mathematically pretty but physically dead. The swampland program is a set of proposed criteria, conjectures, that aim to distinguish the landscape from the swampland. They are rules for what a true, consistent theory of quantum gravity must and must not allow. And here is where our cosmic acceleration hits a potential wall. One of the most discussed swampland conjectures directly challenges the existence of a stable, positive cosmological constant, the simplest form of dark energy. It suggests that in any consistent theory that includes quantum gravity, like string theory, a universe with a true, unchanging vacuum energy that accelerates expansion forever might simply be impossible to construct. Such a universe, according to this view, would reside firmly in the swampland. This is not a minor technicality. It is an existential threat to our standard model of cosmology. Why would this be? Specific conjectures provide the reasoning. The de Sitter conjecture proposes that stable or even long-lived universes resembling de Sitter space, which is the mathematical description of an exponentially accelerating cosmos driven by a cosmological constant, cannot exist in string theory. The potential energy that would drive such acceleration is always unstable, destined to decay. Another, the distance conjecture, states that as you move an infinite distance in the space of field values, an infinite tower of new, ultra-light particles must appear, destabilizing any attempt to maintain a constant vacuum energy. In plainer terms, the machinery of string theory seems to resist creating a universe that just sits still in a state of permanent, gentle acceleration. The equations tend to want to roll downhill, to evolve. If these conjectures hold, then our observed acceleration cannot be due to a simple, eternal cosmological constant. The data forcing us toward a W of -1 would be a cosmic illusion or a temporary snapshot. Instead, the swampland pushes theorists inexorably back toward dynamic models like quintessence. A rolling scalar field, whose energy changes over time, fits much more naturally into the framework of string theory. The acceleration we see today would then be a transient phase in the slow evolution of this field, a momentary pause on a slope, not a permanent plateau. This creates a thrilling, high-stakes tension between theory and observation. Our best measurements keep pointing toward a cosmological constant, but our most ambitious attempt at a theory of everything suggests a cosmological constant might be a mathematical mirage. One side must give. Either the swampland conjectures are wrong, or our interpretation of the data is incomplete, and dark energy is truly dynamic. This battle is not fought in distant galaxies, but in the abstract mathematics of extra dimensions and vibrating strings, yet its outcome will decide the fundamental nature of our expanding reality. The swampland's mathematical pressure toward dynamic fields brings us back to the tangible particles we know exist, particles that might hold a subtle key to the acceleration puzzle. Neutrinos are not just cosmic ghosts, they are real and they are massive. Trillions of these elusive particles stream through your body every second, remnants of the Big Bang and ongoing nuclear reactions in stars. For decades, we thought they were massless, but groundbreaking experiments proved they do have a tiny mass, a discovery that earned a Nobel Prize. This tiny mass changes everything in the cosmic ledger, casting neutrinos in a new role as a form of hot dark matter. The label hot refers to their speed. They were moving at nearly the speed of light when the universe was young. This frenetic motion meant they could smooth out the budding clumps of matter, slightly suppressing the formation of the smallest cosmic structures. Their influence is subtle but measurable in the large-scale distribution of galaxies we see today. So, how could these faint, lightweight particles possibly affect the grand story of cosmic acceleration? The connection lies in their timing and their potential conversations with the unknown. As the universe expanded and cooled, these relativistic neutrinos eventually slowed down, transitioning from hot to cold in their influence. This shift in their behavior injects a specific signature into the expansion history of the cosmos. When cosmologists fit their models to data from the cosmic microwave background and galaxy surveys, they must account for the total neutrino mass. Getting this mass wrong can throw off other derived numbers, including the inferred expansion rate. Some studies suggest that if the total mass of neutrinos is at the higher end of what is currently allowed, it could slightly adjust the early universe physics in a way that increases the predicted value of the Hubble constant, potentially easing the tension with local measurements. It is a delicate balancing act, using one measured quantity to adjust another, but the more speculative and fascinating idea involves a direct dialogue. Could neutrinos and dark energy be talking to each other? In so-called coupled models, dark energy, perhaps as a dynamic quintessence field, could interact not just with gravity, but with neutrinos themselves. As the universe evolves, this interaction could slowly transfer energy between the neutrino sector and the dark energy field, altering how the density of each changes over time. Imagine a seesaw where the weight on one end slowly leaks to the other, changing the balance. Such an interaction could leave a unique fingerprint on how structure forms at different epochs, and on the precise way the expansion rate changed over billions of years. Furthermore, the neutrino mass hierarchy, the still unknown ordering of which of the three neutrino types is the heaviest, could also play a role. Different hierarchies affect how neutrinos behaved in the early universe, which in turn influences the sound horizon scale and other primordial rulers. While these effects are exceedingly small, in the precision cosmology of the 21st century, even the whisper of a neutrino can be a clue. They remind us that the universe is a complex, interconnected system. Solving the mystery of acceleration may not require discovering one monolithic answer, but rather untangling a web of subtle influences, where even the most ghostly particles we know must have their say in the fate of everything. The subtle influence of neutrinos is just one thread in a cosmic tapestry we are learning to read by watching how light itself bends. This bending, a phenomenon called gravitational lensing, offers a direct window into the invisible architecture of the universe and the force that shapes it. when light from a distant galaxy travels across billions of light years to reach us, its path is not perfectly straight. The gravity of all the matter it passes, both the luminous galaxies we see and the vast halos of dark matter surrounding them, subtly warps the fabric of spacetime, acting like a colossal, uneven lens. This distorts the images of the background galaxies, stretching and shearing them into faint, elongated arcs. We are not talking about the dramatic, funhouse mirror distortions produced by massive galaxy clusters, but something far more subtle and pervasive, known as weak lensing or cosmic shear. Across huge patches of the sky, the collective alignment of millions of faint, distorted galaxies reveals a hidden map. It is a map of the cosmic web itself, the dark matter skeleton upon which galaxies are hung. But this map does more than show us where the mass is. It tells us a story about how that structure has grown over the entire history of the cosmos. This is where the mystery of acceleration comes sharply into focus. Dark energy, by pushing space apart, acts as a cosmic brake on the growth of structure. In a universe dominated only by gravity, clumps of matter would attract more matter, and galaxy clusters would grow ever larger and more massive over time. Dark energy's repulsive push counteracts this. As it comes to dominate the cosmos, it makes it harder for new structures to form and slows the growth of existing ones. Weak lensing provides a direct measurement of this suppression. By observing cosmic shear at different distances, we are effectively looking back in time. The lensing pattern from galaxies 10 billion light-years away shows us how clustered matter was in the younger universe. The pattern from galaxies 5 billion light-years away shows a later chapter. By comparing these maps across cosmic epochs, astronomers can measure the rate at which the cosmic web has been growing, or more accurately, the rate at which its growth has been slowing down due to the influence of dark energy. The precise details of this slowdown are exquisitely sensitive to the nature of dark energy itself. A cosmological constant, with its unchanging strength, would suppress structure growth in one specific way. A dynamic quintessence field that evolves would leave a different fingerprint. The key measurement is how the amplitude of the cosmic shear signal changes with both distance and the angular scale on the sky. This two-dimensional map of distortion is a treasure trove of information, encoding the equation of state parameter, W, and potentially revealing whether dark energy interacts with gravity or matter. The challenge, of course, is that the weak lensing signal is incredibly faint. The shear distortion on any single galaxy is tiny, far smaller than the galaxy's own irregular shape. It is only by averaging the alignments of millions of galaxies that the coherent whisper of gravitational distortion rises above the random noise. This is why the next generation of observatories is being built. Missions like the European Space Agency's Euclid telescope and ground-based projects like the Vera-C, Rubin Observatory's Legacy Survey of Space and Time are weak lensing machines of unprecedented power. Euclid, now in space, will image over a third of the sky with razor-sharp infrared vision, measuring the shapes and distances of billions of galaxies. The Rubin Observatory will perform a decade-long deep scan of the southern sky, creating the largest cosmic movie ever made. Together, they will construct the most detailed three-dimensional mass map of the observable universe, charting the growth of structure across 10 billion years with statistical precision we can scarcely imagine today. Their goal is not just to confirm dark energy exists, but to measure its equation of state to within 1%, and to test whether that number has changed over time. They will tell us, definitively, if the accelerating force is a constant feature of the vacuum or a dynamic actor in the cosmic play. In the subtle, twisted light of distant galaxies, we may finally find the signature that reveals what our universe is truly made of and where it is ultimately going. This three-dimensional map of mass, built from twisted light, is not our only cosmic ruler. There is another, etched with even greater precision into the very distribution of galaxies themselves. It is called baryon-acoustic-oscillations, and it is a fossilized echo of sound from the universe's first 300,000 years. To understand this, we must listen to the cosmos when it was a seething, opaque fluid. After the Big Bang, the universe was an intensely hot plasma, a soup of protons, electrons, and light, all tightly coupled. In this dense medium, gravity acted as the great compressor, trying to pull matter into clumps. But the intense radiation pressure from the sea of photons pushed back, creating a powerful outward force. This tug-of-war between gravity's inward pull and radiation's outward push set up rhythmic pressure waves, literal sound waves, that rippled outward through the primordial plasma at over half the speed of light. These were not gentle ripples, but powerful spherical tsunamis of compression and rarefaction, moving matter in their wake. Then, a cosmic moment of quiet. When the universe cooled enough for atoms to form, the electrons were captured and the fog cleared. The photons, now decoupled, streamed freely as the cosmic microwave background. The sound waves stopped dead in their tracks, frozen. What they left behind was a distinct, predictable pattern. Each wave had pushed a shell of ordinary matter, baryons, ahead of it like snow before a plow. When the music stopped, that shell of matter was left at a specific radius from the original density seed. That radius, the distance the sound could travel before the universe became transparent, is our standard ruler. It is about 500 million light-years in today's universe. After this freeze frame, gravity took over. The overdense seeds, now surrounded by these spherical shells of matter, grew into the galaxies and clusters we see today. The breathtaking result is that galaxies today are ever so slightly more likely to be found separated by this specific scale, the imprint of that ancient sound horizon. It is as if the cosmos is stamped with a faint, regular grid, a whisper of its infancy. This is the baryon-acoustic-oscillation signal. We detect it not by looking at individual galaxies, but by statistically analyzing the positions of millions of them from massive surveys. By measuring the apparent size of this ruler at different distances, we chart the expansion history of the universe with phenomenal accuracy. When we look at galaxies 5 billion light-years away, we are seeing the universe at a younger age. The baryon-acoustic-oscillation ruler at that epoch appears to us at a certain angular size on the sky. By comparing that to the ruler's known true physical length, we can calculate exactly how much the universe has stretched between then and now. We can do this for multiple cosmic epochs, building a step-by-step timeline of the expansion rate. This is a direct, geometric measurement, independent of the brightness of stars or supernova. Its power is immense. When combined with the distance measurements from Type 1, a supernova, the two methods form a devastatingly precise cross-check. Supernova give us the luminosity distance, how much the light has been dimmed by expansion. Baryon-acoustic-oscillations give us the angular diameter distance, a direct geometric measure of cosmic stretching. Together, they lock down the properties of dark energy with a vice-like grip. The data from baryon-acoustic-oscillations strongly confirms the accelerating expansion. More importantly, it constrains the equation of state parameter, W, to be incredibly close to -1, cornering the simple cosmological constant model. It tells us that if dark energy is dynamic, its evolution has been very, very slow. This fossilized sound is now one of the foundational pillars of modern cosmology, a ruler born from the universe's first cry, used to measure its silent, accelerating flight. That fossilized sound from the early universe provides a geometric backbone, but the original, shocking evidence for acceleration came from watching stars die. In 1998, two independent teams of astronomers made a discovery that would redefine cosmology. They were not looking for a mysterious new force. They were trying to measure how much the universe's expansion was slowing down. Everyone expected the gravity of all the matter in the cosmos to be putting the brakes on the Big Bang's initial push. To measure this deceleration, they needed to see how fast galaxies were receding at different distances, which required knowing those distances with extraordinary precision. Their tool was a specific kind of stellar catastrophe, the Type 1, a supernova. These explosions occur in binary star systems where a dense white dwarf siphons material from a companion star. Once the white dwarf reaches a critical mass, about 1.4 times that of our Sun, it triggers a runaway thermonuclear explosion. This precise trigger point is the key. Because the explosion always happens at almost exactly the same mass, these supernovae always release nearly the same amount of light. They are not perfectly identical, but their peak brightness is so consistent that by measuring how quickly they brighten and fade, astronomers can calibrate their true, intrinsic luminosity. This makes them phenomenal standard candles. You know how bright the explosion truly is, so by measuring how dim it appears from Earth, you can calculate its exact distance. The teams, led by Saul Perlmutter and by Brian Schmidt and Adam Rees, painstakingly searched for these distant beacons. They found dozens of Type 1, a supernova billions of light years away. In galaxies so far, they showed us the universe when it was much younger. When they plotted the distances against the recession speeds of the host galaxies, they expected to see the curve showing a slowdown. Instead, the data revealed the opposite. The most distant supernova were fainter than they should have been if the universe's expansion had been slowing down or even coasting at a constant rate. The only explanation was that the expansion was speeding up. Some unknown repulsive force, later dubbed dark energy, was pushing galaxies apart faster and faster. It was a result so unexpected that the teams spent years checking and rechecking for errors. The universe was not just expanding, it was accelerating, a finding that earned them the Nobel Prize in Physics in 2011. In the decades since, this revolutionary discovery has been tested and refined on a monumental scale. Surveys like Pan-STARRS in Hawaii and the monumental Dark Energy Survey in Chile have scanned huge swaths of the sky, discovering not dozens, but thousands of Type 1, a supernova. This avalanche of data has confirmed the reality of acceleration beyond any reasonable doubt. Yet, paradoxically, this wealth of precision has also sharpened the Hubble tension. As the local supernova measurements have become exquisitely precise, their calculated value for the expansion rate has solidified, stubbornly remaining higher than the rate predicted from the early universe. The very tool that discovered dark energy is now highlighting a deep inconsistency in our cosmic model. This forces astronomers to scrutinize the supernovae themselves for hidden flaws. Could there be subtle, unaccounted for systematic uncertainties muddying the signal? Two major concerns linger. The first is cosmic dust, interstellar dust within the supernova's host galaxy, or dust floating in intergalactic space, can dim and redden the light of the explosion, making it appear farther away than it truly is. Modern surveys now observe supernovae in multiple colors, from ultraviolet to infrared, to model and subtract this extinction effect. The second, more profound worry is supernova evolution. Are the explosions that happened 9 billion years ago, when the universe was younger and stars had different chemical compositions, truly identical to the ones we see today? If the peak luminosity of these ancient standard candles was slightly different, it would throw off our entire cosmic distance ladder. So far, the data suggests remarkable uniformity across cosmic time, but it remains an active area of intense study. These supernovae, these brilliant dying stars, remain our most direct witnesses to the accelerating universe. Their fading light, a constant reminder that our deepest discoveries often lead to even deeper mysteries. The brilliant deaths of supernovae gave us our first glimpse of the accelerating universe, but to understand the subtle influence of this force, we must listen to an even older whisper, one that has been traveling for 13.8 billion years. This whisper, the cosmic microwave background, holds a faint secondary signature of dark energy's work, an imprint called the late-time integrated Sachs-Wolf effect. To grasp this, picture a single photon from that ancient afterglow beginning its journey to us. It is not traveling through empty, static space. Its path weaves through the evolving cosmic web, the vast hills and valleys of gravitational potential created by superclusters of galaxies and the voids between them. As the photon climbs out of a deep gravitational well, a region of high density, it must expend energy, like a ball rolling uphill. In a universe where gravity alone dictates expansion, these wells would deepen over time as matter clumps together. The photon would lose energy on the way in and gain exactly the same amount back on the way out, with no net change by the time it reaches us. But dark energy changes the rules. Its repulsive push counteracts gravity, causing the cosmic web to smooth out over time. Those gravitational wells become shallower as the universe accelerates. When our CMB photon falls into a well that is later shallower than when it entered, it does not get all of its energy back on the climb out. The photon arrives at our telescopes slightly colder, with a tiny bit less energy than it would have in a universe without dark energy. Conversely, a photon crossing a large void, a gravitational hill, might find that hill has flattened, leaving it with a bit of extra energy, appearing slightly hotter. This subtle, late-time gain or loss of energy in the CMB photons is the integrated Sachs-Wolf effect. It is a direct imprint of the changing gravitational landscape over the last several billion years, a change driven by the onset of cosmic acceleration. We cannot see this effect in a single photon, of course. The temperature shift is minuscule, buried in noise. To find it, cosmologists use a statistical trick. They look for a specific correlation between two maps of the universe. The first map is the temperature of the cosmic microwave background across the sky. The second is a map of the large-scale structure of the more recent universe, showing where galaxies and mass are concentrated today. If dark energy is flattening gravitational potentials, then the coldest spots in the CMB should statistically align with the locations of the most massive superclusters, where photons lost extra energy climbing out of shallowing wells. The hottest CMB spots should align with the largest voids. This cross-correlation is the smoking gun. Detecting it is a monumental challenge, requiring exquisitely clean maps from both the CMB, like those from the Planck satellite, and enormous galaxy surveys. After years of painstaking work, astronomers have indeed found this correlation. The signal is there, a faint but statistically significant whisper that confirms the universe's gravitational potentials are indeed evolving as predicted by a model that includes dark energy. It is an independent, elegant confirmation that something is altering the cosmic growth rate. However, the strength of this detected signal is where intrigue deepens. In some analyses, the measured correlation appears slightly stronger than what the standard lambda CDM model with a simple cosmological constant predicts. It is not a definitive discrepancy, but it is a tantalizing hint. Could this mean dark energy's influence on structure is even more pronounced than we thought? Or does it point to a more complex interaction, perhaps between dark energy and dark matter, or a modification to gravity that enhances the smoothing of the cosmic web? The integrated Sachs-Wolf effect is a subtle probe, sensitive to the entire history of structure formation. Its tentative whispers do not yet overthrow the standard model, but they add another layer of nuance to the mystery, suggesting that the story of cosmic acceleration is written not just in the expanding distances between galaxies, but in the fading echoes of gravity's own once dominant voice. The subtle whispers of the integrated Sachs-Wolf effect are a powerful clue, but they still rely on interpreting the statistical echoes of the past. What if we could watch the universe accelerate in real time? This is the promise of redshift drift, a futuristic experiment so direct it is sometimes called the Sandage test. For nearly a century, we have measured the expansion by looking at the redshift of galaxies, the stretching of their light toward the red end of the spectrum caused by the expansion of space between us and them. That tells us how fast they are moving away right now. Redshift drift asks a more dynamic question: how is that speed changing? Imagine watching a single, distant galaxy not for a night, but for decades. In a universe coasting at a constant speed, its redshift would remain perfectly stable. In a universe slowing down under gravity, the redshift would actually decrease over time as the galaxy's recession speed gradually diminished. But in our accelerating universe, the prediction is clear and unique. The redshift of that distant galaxy should increase. Its light should become redder and redder as the repulsive push of dark energy drives it away from us faster and faster with each passing year. It would be like watching a ship on the horizon, and instead of its horn fading at a steady pitch, the sound drops deeper and deeper as the ship not only moves away, but also continuously guns its engine. This is a direct, model-independent test. It does not rely on standard candles, cosmic rulers, or complex theories of gravity. It is a pure kinematic measurement, a literal speedometer for the cosmos, tracking how the velocity of the universe itself changes over a human lifetime. The effect, however, is vanishingly small. For a galaxy several billion light-years away, the change in redshift over a decade might be only 1 part in a billion, a shift far smaller than the width of a single spectral line. Detecting this requires a monumental leap in precision, stability, and patience. It demands instruments that do not yet fully exist, like the Extremely Large Telescope, or ELT, currently being built in Chile. With a primary mirror spanning 39 meters, this behemoth will collect enough light to observe the faint, specific absorption lines in the spectra of distant quasars with unprecedented clarity. It will then need to measure those same lines again, 10 or 20 years later, with a stability that can discern a shift equivalent to a snail's pace on the other side of the solar system. The entire experiment is a testament to long-term scientific vision. A positive detection would be a breathtaking confirmation, not just of expansion, but of acceleration itself, witnessed as it happens. It would transform dark energy from a conclusion drawn from ancient light into a dynamic phenomenon we can watch unfold in the present tense, a slow-motion revelation of the universe's accelerating heartbeat. That real-time speedometer for the cosmos faces a fundamental challenge right here in our own cosmic neighborhood. Measuring the universe's expansion locally is not as simple as pointing a telescope and reading a speed. The smooth, majestic river of the Hubble flow, where space itself stretches and carries galaxies apart, is muddied by chaotic, local currents. These are the peculiar velocities of galaxies, the individual motions they have on top of the cosmic expansion, imparted by the gravitational tug of war happening all around us. Think of it like leaves floating on a wide, steadily flowing river. The river's current is the Hubble flow, carrying all leaves downstream. But if a leaf is caught in a small whirlpool near the bank, or pulled toward a group of other leaves clumped together, it will have its own skittering motion on top of the downstream drift. That skitter is its peculiar velocity. For galaxies, these peculiar motions are caused by the lumpy distribution of mass in the universe. A galaxy will feel a gravitational pull toward any large concentration of mass nearby. Our own Milky Way, for instance, is not just drifting with the Hubble flow. We are being pulled toward the immense gravitational weight of the Great Attractor, a mysterious region of space hundreds of millions of light-years away that is drawing in thousands of galaxies, including our own local group. Our solar system moves around the galaxy moves within the local group, and the entire local group is falling toward the Virgo cluster, which itself is being pulled toward the Great Attractor. All of this complex, local dancing happens on top of the grand, smooth stretch of space. This creates a serious problem for astronomers trying to measure the Hubble constant locally. When we look at a nearby galaxy and measure its redshift, we are seeing the combined effect of its motion due to the Hubble expansion and its own peculiar velocity. If we mistake a galaxy's infall toward a massive cluster for part of the Hubble flow, we will get its distance and speed relationship wrong. To get a clean measurement of the pure expansion rate, we must somehow subtract these local gravitational dances from the total observed motion. It is a monumental task of cosmic accounting. Astronomers use sophisticated models of the large-scale structure of the universe, mapping the distribution of galaxies and dark matter to predict the expected gravitational pulls and the peculiar velocities they induce. They then correct their measurements of galaxy distances and speeds accordingly. But these models are only as good as our maps, and our maps of the cosmic web, especially in our nearby universe, are still incomplete. Could errors in this accounting be a major contributor to the Hubble tension? Could the faster expansion rate measured locally be because we have not fully corrected for some vast, unseen flow pulling our entire neighborhood of galaxies? Some researchers have proposed that we might be in a larger-than-expected region of peculiar motion, a local Hubble bubble not of density, but of velocity. If our local group is caught in a faster-than-average stream within the cosmic flow, our local measurements would be biased high, while the early universe measurement from the CMB, which sees the pristine, smooth average, would remain unaffected. This idea is scrutinized intensely. The CMB itself provides a reference frame. The tiny dipole anisotropy, the hot and cold spots caused by our motion relative to the ancient light, tells us our net peculiar velocity through the cosmos. While large, this measured velocity is consistent with the pull from known structures like the Great Attractor and the even larger Shapley supercluster beyond it. The question is whether there are still larger, unseen overdensities farther out that could be adding an extra, unaccounted for kick to our local motion. Disentangling the smooth river from the local whirlpools is perhaps the most delicate and crucial step in measuring our universe's present-day expansion. It forces a humbling realization that to see the grand, simple motion of space itself, we must first understand every gravitational handshake in our immense cosmic neighborhood. The fate of those intricate galactic dances is sealed by the relentless push of dark energy, while today the universe is a vibrant tapestry of clustered galaxies and vast superclusters. The future written by acceleration is one of profound isolation. To understand this, we must consider the cosmic tug-of-war on the grandest scales. Galaxy clusters are the largest gravitationally bound structures in existence, colossal cities of thousands of galaxies held together by the immense gravity of their combined dark matter. Their formation was a slow, billion-year process, where the mutual attraction of matter gradually overcame the expansion of space, pulling galaxies together into these dense knots. For most of cosmic history, gravity was winning, but the era of acceleration has changed the rules of the contest. Dark energy's repulsive force acts as a counterweight. While it cannot instantly tear apart a tightly bound cluster, it puts an absolute ceiling on growth. Think of a climber trying to scale a cliff while the rock face itself is slowly, steadily sliding outward. As the universe's expansion accelerates, the space between separate clusters and superclusters stretches at an ever-increasing rate. The raw material for building new colossal structures, the gas and galaxies that have not yet fallen into a cluster's grasp, is being carried away faster than gravity can pull it in. The growth of new galaxy clusters has already effectively stopped. Our universe will build no more cities of this scale. The far future holds an even more dramatic dissolution. If dark energy is a cosmological constant, its strength remains fixed while the density of matter within clusters continues to dilute as the universe expands. Billions of years from now, the repulsive force will no longer just halt growth. It will begin to overwhelm the binding gravity at the very outskirts of these massive structures. Simulations show this process with chilling clarity. First, the tenuous filaments of the cosmic web that feed clusters will be severed, stranding them. Then, the clusters themselves will begin to evaporate from the outside in. Galaxies on the outer edges will find the space around them stretching so violently that the cluster's gravity can no longer hold them. They will be stripped away, one by one, like leaves torn from a tree in a hurricane, flung into the ever-darkening void. Each departing galaxy will find itself utterly alone, with every other island of light receding over a horizon of expanding space, their light stretched into invisibility. Eventually, even the core galaxies of a cluster will be pulled apart. This is not the violent shredding of the Big Rip, but a slow, inexorable unraveling over trillions of years, a future where the largest structures gravity ever built are patiently dissolved by the silent, constant energy of the vacuum. This lonely fate is the direct consequence of the acceleration we measure today. It paints a picture of a cosmos growing cold and dark, not with a catastrophic bang, but with a whisper of infinite expansion. The vibrant, clustered universe we see through our telescopes is a transient spectacle, a brilliant but fleeting chapter in a story that ends in quiet, empty separation. That slow dissolution of cosmic structure into lonely isolation points to a terrifyingly fine-tuned balance. If the repulsive force of dark energy were even slightly stronger, the universe would have blown itself apart before any stars could ever ignite. This razor's edge leads to one of the most controversial and mind-bending explanations of all, the multiverse. The idea emerges from the mathematical heart of string theory, which suggests not one universe, but a vast, perhaps infinite, landscape of possible universes. Each of these universes would have its own random, fundamental constants, including a different value for the vacuum energy, or cosmological constant. In this infinite cosmic lottery, most universes would have a cosmological constant that is either immensely positive or deeply negative. A large positive value would cause runaway expansion so violent it prevents any structure from ever forming. A large negative value would cause the universe to collapse back on itself in a big crunch almost instantly. In such chaotic landscapes, galaxies, stars, planets, and life are impossible. But in an infinite array of possibilities, there will be a tiny, tiny fraction of universes where the cosmological constant, by sheer random chance, landed very close to zero. In those exceptionally rare cosmic habitats, expansion is gentle enough to allow gravity to pull matter into galaxies and stars, yet present enough to eventually drive acceleration. We, of course, find ourselves in one of those habitable universes. This is the application of the anthropic principle. It states that the observed values of the universe's fundamental constants are not determined by a unique, elegant theory, but are instead a selection effect. We can only observe the constants that allow for our existence as observers. It answers the question of why our cosmological constant is so inexplicably small by saying, if it weren't, we wouldn't be here to ask the question. This idea is both profoundly influential and deeply unsettling to many scientists. On one hand, it offers a potential escape from the fine-tuning problem, reframing it as a cosmic coincidence of our address. On the other, it feels like a retreat from the traditional goal of physics, which is to find a single, compelling, predictive reason for why the universe is the way it is. If any value is possible somewhere in the multiverse, have we explained anything at all, or simply shifted the mystery to an unobservable realm? The debate rages between those who see the anthropic principle as a necessary Copernican humility, accepting that our universe is not special, just survivable, and those who see it as a philosophical surrender that halts the search for a deeper, testable theory. It forces a stark choice. Is the unnerving smallness of dark energy a clue to a beautiful, yet to be discovered law, or is it merely our local zoning code in a chaotic, infinite metropolis of realities? The multiverse offers a sweeping, philosophical answer, but other theories search for a specific, physical trigger within our own cosmos. One of the most elegant of these dynamical models is called vacuum metamorphosis. This idea proposes that dark energy is not a constant feature of empty space, but a phase transition that awakened at a specific moment in cosmic history, a fundamental shift in the nature of the vacuum itself. The trigger, remarkably, might be linked to the most ghostly particles we know, neutrinos. The theoretical motivation springs from a deep question in quantum gravity. As the universe expands and cools, the behavior of matter and fields changes. In the vacuum metamorphosis model, there is a critical threshold tied to the total mass of neutrinos in the universe. When the average matter density of the cosmos drops below this neutrino mass threshold, the vacuum of space undergoes a metamorphosis. Its properties change, like water freezing into ice. Before this transition, the vacuum energy was effectively zero, lying dormant. After it, the vacuum acquires a constant energy density, essentially turning on the cosmological constant we observe today. It is as if the universe has two different ground states, and the collective mass of all the neutrinos acts as the switch that flips it from one state to the other. This provides a natural, physical explanation for the coincidence problem. Dark energy did not dominate from the beginning, nor did it awaken at a random time. It emerged precisely when the density of matter, dictated by expansion, fell past a value set by a fundamental particle property. The model makes a sharp, testable prediction for when this should have happened, at a redshift of about 5, corresponding to when the universe was roughly 1/3 of its current size. This timing aligns well with our observations that acceleration became significant around 5 billion years ago, but the true power of vacuum metamorphosis lies in its distinct fingerprints on the cosmos, particularly in how it affects the growth of structure. In the standard cosmological constant model, dark energy's influence on structure growth is a slow, steady suppression. In vacuum metamorphosis, the story is different. Before the transition, the universe expands as if there is no dark energy at all, allowing structures to form more robustly under pure gravity. Then, at the moment of metamorphosis, the cosmological constant switches on abruptly. This sudden injection of repulsive energy acts like a brake slammed on the growth of cosmic web. The result is a specific, measurable suppression in how quickly galaxy clusters and superclusters form after that redshift. This leaves a unique signature in the large-scale distribution of galaxies and in the weak gravitational lensing of distant light, a signature that upcoming surveys like Euclid and the Vera see. Rubin Observatory are exquisitely designed to detect if the growth of structure shows a sharper decline than predicted by a simple, always-on cosmological constant. Vacuum metamorphosis could be a compelling culprit. It elegantly ties together the neutrino sector, the onset of acceleration, and the observed large-scale structure of the universe, offering a testable, physical narrative for why our cosmos began to run away from itself at a specific moment in time. But what if dark matter and dark energy are not separate entities at all? This radical idea proposes that the two greatest mysteries of cosmology are actually two faces of a single, exotic substance. These are unification models, and perhaps the most famous candidate is known as the Chaplygin gas. Imagine a fluid that can change its fundamental nature over cosmic time. In the dense, early universe, this fluid would behave just like cold, dark matter, clumping together under gravity to seed the formation of galaxies and clusters. Then, as the universe expands and thins out, this same fluid undergoes a dramatic transformation. It stops acting like attractive matter and instead develops a strong negative pressure, driving the accelerated expansion we see today. It is the ultimate cosmic chameleon, a unified dark fluid that solves two puzzles with one elegant ingredient. The original Chaplygin gas model, inspired by aerodynamics, has a very specific equation of state. Its pressure is inversely proportional to its density. This mathematical relationship creates the desired behavior. When the gas is dense, its pressure is low, allowing it to cluster like dust, which is how cosmologists model cold, dark matter. When the gas becomes diffuse as the universe expands, its pressure plummets into strongly negative territory, mimicking a cosmological constant. The appeal is breathtaking. Instead of a universe composed of 27% mysterious dark matter and 68% even more mysterious dark energy, we have a single component accounting for 95% of everything, its behavior smoothly transitioning as the cosmos ages. It promises a cleaner, more parsimonious universe. However, elegance in theory must survive the brutal scrutiny of observation, and the Chaplygin gas faces monumental challenges. The first major hurdle is the cosmic microwave background. The precise peaks and troughs in the CMB's temperature fluctuations are a sensitive record of how matter and radiation interacted in the first 400,000 years. A unified fluid that acts like dark matter must replicate the exact same acoustic oscillations that standard cold dark matter produces, while some generalized Chaplygin gas models can be tuned to roughly match the CMB power spectrum. The fit is often not as precise or natural as the standard two-component model. The constraints are extremely tight, pushing the model's parameters into very specific corners, but the most damning evidence comes from the realm of galaxy clusters and the large-scale structure we see today. In the standard model, dark matter is collisionless, meaning dark matter particles and halos can pass right through each other. This is crucial for explaining observations of colliding galaxy clusters, like the Bullet cluster, where the mass, traced by gravitational lensing, is clearly separated from the hot gas that slows down due to friction. A unified fluid like the Chaplygin gas, however, has a continuous, smooth pressure. This pressure supports the fluid against gravitational collapse on small scales. In practical terms, it struggles to form the dense, compact dark matter halos that we observe surrounding individual galaxies. It also tends to suppress the formation of structure on smaller scales, leading to a cosmic web that looks too smooth compared to the lumpy, richly detailed distribution of galaxies we actually see. Furthermore, the sound speed in such a fluid can become problematic. As it transitions to its dark energy phase, perturbations in the fluid can travel faster, potentially wiping out small-scale structures that have already formed. This is a fatal flaw for a substance that needs to act like silent, clustering dark matter for billions of years before switching roles, while later variants, like the generalized Chaplygin gas, introduce more parameters to try and navigate these observational minefields. They often begin to lose the very simplicity that made the idea appealing in the first place. The dream of a single dark fluid remains a powerful intellectual lure, a testament to our desire for cosmic unity. Yet the universe, in its detailed fossil record of light and structure, seems to insist on a more complex, divided dark sector. This does not kill the idea of interaction, but it suggests that if dark matter and dark energy are connected, their relationship is likely more subtle than a simple shared identity. The dream of a unified dark fluid may have faded, but another profound idea emerges from the very bedrock of theoretical physics. The holographic principle suggests a reality so strange it redefines the nature of information itself. It posits that all the information contained within a three-dimensional volume of space can be perfectly described by a theory that lives on its two-dimensional boundary, like a cosmic hologram. Our three-dimensional reality, with all its richness, might be a projection from information encoded on a distant surface. This is not science fiction, but a serious consequence of combining quantum mechanics and gravity, born from the study of black holes. When applied to the entire cosmos, this principle yields a startling and specific prediction for dark energy, known as holographic dark energy. If the universe obeys holographic bounds, then the total energy in any region should not be proportional to its volume, but to the area of its boundary. This places a fundamental limit on how much dark energy can be contained within our observable universe. The density of this holographic dark energy is not a random constant, but is inversely proportional to the square of a specific cosmic length scale. But which scale? This is where the theory branches into two fascinating and competing possibilities. The first candidate is the Hubble radius, the distance beyond which galaxies recede from us faster than light due to the expansion of space itself. It is a natural, evolving horizon that defines our causal patch of the universe. If the holographic cutoff is tied to this radius, the dark energy density evolves with the expansion rate in a unique way. The second, more intriguing candidate is the future event horizon. This is not a boundary we can see today, but a destiny. It is the farthest distance from which light emitted now will ever reach us in the infinite future, given the accelerating expansion. As time passes, this horizon grows. If the holographic dark energy density is tied to this future boundary, it creates a profound feedback loop, where today's dark energy density depends on the ultimate future fate of the cosmos. This introduces a cosmic circularity that is both elegant and puzzling. The predictions of these models are distinct and testable. Holographic dark energy typically behaves like a dynamical form of quintessence, with an equation of state parameter, W, that evolves over time. It often predicts that W is slightly greater than -1 in the past and becomes less than -1 in the future, potentially veering into the phantom regime and heading toward a big rip. This evolution leaves fingerprints in the growth of cosmic structure and in the detailed shape of the baryon-acoustic-oscillation signal. However, holographic dark energy faces significant challenges when confronted with precise observational data. The model tied to the Hubble radius often struggles to produce enough acceleration to match what we observe. The model tied to the future event horizon, while more successful, introduces a causality concern that makes many physicists uneasy. How can the current energy density of the universe, which determines local physics and the very expansion rate, depend on the integral of that expansion all the way to the infinite future? It suggests the present is being determined by the future, a concept that feels at odds with our understanding of cause and effect. Furthermore, fitting the model to the exquisite data from the cosmic microwave background and supernovae often requires adding extra parameters or adjustments, making it less simple and compelling than the cosmological constant it seeks to replace. Yet, the power of the holographic idea is undeniable. It does not invent a new, ad hoc field or particle. Instead, it derives the properties of dark energy from a fundamental limit on information, a principle that emerges from our deepest attempts to reconcile quantum theory with gravity. Even if the specific models falter, they point toward a revolutionary possibility that the acceleration of the universe is not an arbitrary feature, but a direct consequence of the universe's hidden holographic nature, a cosmic projection whose rules we are only beginning to decipher. This holographic projection of reality rests on a smooth, cosmic canvas, but our universe is anything but smooth. We have built our entire story of acceleration on a foundational assumption that on the largest scales, the cosmos is homogeneous and isotropic. This is the cosmological principle, the idea that if you zoom out far enough, the lumpy distribution of galaxies and vast voids averages out into a uniform soup. It is this smoothness that lets us write the simple, elegant equations of general relativity that describe an expanding universe. But what if this assumption, this very bedrock of modern cosmology, is the source of our greatest error? The universe we observe is a tapestry of extreme contrasts. Gigantic voids, hundreds of millions of light-years across, contain almost nothing. Dense filaments and massive galaxy clusters thread between them, where matter is concentrated 1,000 times more densely. We do not live in a smooth fluid, we live in a complex, Swiss cheese structure. The question is whether treating this lumpy reality as a smooth average is a harmless simplification, or a catastrophic oversight that creates the illusion of dark energy. This is the backreaction hypothesis. The core idea is that the gravitational effects of these inhomogeneities do not simply average out. When you try to describe this lumpy universe with smooth equations, the lumps fight back. They backreact on the average expansion rate. Think of a ball rolling down a bumpy hill versus a smooth slope. On the smooth slope, its average speed is easy to predict. On the bumpy hill, it will speed up over bumps and slow down in dips. If you only measured the ball's final position and time and assumed a smooth slope, you might conclude some mysterious force was pushing it. In cosmology, the bumps are the dense clusters and the dips are the vast voids. The expansion rate inside a deep void is faster than the cosmic average because there is less gravity holding it back. Inside a dense cluster, expansion is slower. When we try to paste these different regions together into a single, smooth model, the mathematics becomes fiendishly complex. The average expansion rate we derive from our smooth equations might not match the true average of all these wildly different regions. Proponents of backreaction argue that this mismatch could be significant. The effect, they suggest, is that the observed average expansion accelerates over time, not because of a new energy component, but because voids come to dominate the volume of the universe. As the cosmos evolves, voids grow and merge, occupying more and more of space. These fast-expanding regions become the cosmic majority. When we take a simplistic average, the increasing influence of these voids could mimic the signal of a dark energy-driven acceleration. It is a compelling argument from pure geometry and gravity, requiring no new physics. However, the devil is in the mathematical details, and those details are extraordinarily difficult to calculate. General relativity is notoriously nonlinear, meaning the whole is not simply the sum of its parts. You cannot just average the expansion rates of a void and a cluster to get the global rate. The coupling between regions, the way curvature and density interact across boundaries, makes the full calculation a monumental task in theoretical physics. Researchers build complex models, often using Swiss cheese constructions with spherical voids embedded in a smooth background, to try and estimate the magnitude of this backreaction effect. The current consensus, after decades of work, is that while the effect is real and non-zero, it is almost certainly too small. The most rigorous calculations to date suggest that backreaction from cosmic structures might alter the inferred expansion history by at most a few percent. This is far from the roughly 70% contribution needed to explain the observed acceleration. It might be a small correction to our equations, a subtle footnote in the cosmic ledger, but not the protagonist of the story. The smooth cosmological principle, it seems, survives this assault. The acceleration signal is too strong, too cleanly measured across multiple independent probes, to be dismissed as a mere artifact of improper averaging. Yet the effort is far from wasted. It forces a crucial refinement of our models. As we enter the era of precision cosmology with telescopes like Euclid, we must account for these small backreaction effects to extract the true signal of dark energy. The lumps and voids are not creating the mystery, but they are whispering around its edges, reminding us that the universe's beautiful simplicity is always an approximation of its magnificent, intricate complexity. The intricate lumpiness of our cosmic neighborhood hints at a deeper, more unsettling possibility. What if the universe's acceleration is not the only sign that our standard, smooth model is incomplete? There are whispers in the oldest light we can see, anomalies so strange they have been given a dramatic name, the axis of evil. These are not small, statistical flukes in the cosmic microwave background, but large-scale patterns that defy our expectations of a perfectly random, isotropic cosmos. The most famous is an apparent alignment, when scientists decompose the CMB's temperature map into its fundamental components, called multipoles. The very largest scales, the quadrupole and octupole, show a puzzling coherence. Their hot and cold spots seem oddly aligned with each other and with the plane of our solar system. It is as if the universe's earliest structure has a faint, preferred direction, a cosmic axis. This is profoundly unexpected. The standard model predicts these primordial fluctuations should be completely random, with no special direction whatsoever. The chance alignment we see is statistically unlikely, around 1 in 1,000. Another major anomaly is the hemispherical power asymmetry. One half of the CMB sky appears to have slightly stronger temperature fluctuations than the other half. It is a lopsided universe, with more action in one hemisphere than the other. These are not artifacts of poor data. They have persisted through multiple satellite missions, from WMAP to Planck, surviving intense scrutiny. So what could they mean? One radical interpretation connects them directly to the mystery of dark energy. Perhaps the force driving acceleration is not a perfectly uniform cosmological constant, but a dynamic field, like quintessence, that began its evolution with a slight directional preference, an anisotropy imprinted at the dawn of time. This field would have influenced the very first moments of inflation, the period of hyper-expansion that seeded all structure. If the field had a preferred direction, it could have stretched space slightly more in one direction than another, creating a faint but persistent axis in the primordial density variations. That same field, rolling to its present state, could then be the source of today's dark energy. In this view, the axis of evil is not a separate mystery, but a fossil from the birth of the accelerating agent itself. Alternatively, these anomalies might point to something even more fundamental, a crack in the cosmological principle. We assume the universe is the same in every direction, but the CMB hints it might not be. If the universe is genuinely anisotropic on its largest scales, then our smooth equations for expansion are an oversimplification. The acceleration we measure could be slightly different in one direction than another, a subtle effect that future surveys might one day detect. These whispers from the infant cosmos are too faint to overthrow our models, but they are too persistent to ignore. They suggest that the story of cosmic acceleration may be woven into a more complex, and perhaps slightly directional, tapestry of reality than we have dared to imagine. These whispers of cosmic asymmetry lead us back to the quantum vacuum, the very fabric of empty space that may hold the secret to acceleration. The vacuum in quantum field theory is not a serene nothingness, it is a seething, turbulent sea. This is because of a fundamental principle called zero-point energy. Even at absolute zero, when all classical motion ceases, quantum fields cannot sit still. They are subject to Heisenberg's uncertainty principle, which forbids them from having both a definite position and a definite momentum of zero. The result is that every field, everywhere, undergoes perpetual, random fluctuations. Virtual particle-antiparticle pairs wink into existence, borrowing energy from the vacuum for an incredibly brief moment before annihilating each other and returning it. This endless dance happens for every possible type of particle and every possible mode of vibration. To calculate the energy density of this quantum vacuum, you must theoretically sum the contributions from every single one of these fluctuations across all frequencies. And here lies the catastrophe. When you perform this sum, the answer you get is infinite. An infinite vacuum energy would produce a repulsive gravitational force so strong it would have curvatured the universe into oblivion instantly. Clearly, this is not our reality. Physicists have a powerful, if somewhat procedural, tool to deal with such infinities, a process called renormalization. The idea is that the infinite, bare value is not physically meaningful. Instead, we recognize that our theories have a limited range of validity. We introduce a cutoff scale, a maximum energy or minimum distance beyond which our current physics, like the Standard Model, no longer applies. This cutoff could be at the Planck scale, where quantum gravity becomes essential, or at the scale of some new physics-like grand unification. We then calculate physical, measurable quantities relative to this cutoff. The hope is that when we eventually have a complete theory, the infinities will cancel in a natural way, leaving a finite, small result. But for the cosmological constant, this process fails spectacularly. Even if we set the cutoff at a reasonable scale, like the electroweak scale, where the Higgs field operates, the predicted vacuum energy is still about 120 orders of magnitude larger than the tiny value we observe for dark energy. This is not a minor miscalculation, it is the worst prediction in the history of science. So where does this leave us? One compelling possibility is that dark energy is not the full quantum vacuum energy, but a low-energy remnant or shadow of a more complete, symmetric theory. The leading candidate for such a theory is supersymmetry. Supersymmetry proposes a profound partnership in nature, that every known particle has a superpartner with a different spin. This elegant symmetry would cause the contributions of fermions and bosons to the vacuum energy to be perfectly opposite in sign. In a perfectly unbroken, supersymmetric universe, the positive energy from bosonic fluctuations and the negative energy from fermionic fluctuations would cancel exactly, resulting in a zero cosmological constant. Our universe, however, is not supersymmetric at low energies we can access. If it exists, supersymmetry must be broken at some high-energy scale. When a symmetry breaks, the perfect cancellation is spoiled, but it can leave behind a tiny residual. The energy scale of this breaking determines the size of the leftover vacuum energy. If supersymmetry breaks at the electroweak scale, the remnant vacuum energy could be around the observed value of dark energy. It is a beautiful idea, a broken symmetry leaving behind a faint echo that now drives the cosmos apart. Yet, despite decades of searching, particle colliders like the Large Hadron Collider have found no direct evidence for supersymmetric particles at the expected energies. Their continued absence pushes the possible supersymmetry breaking scale higher, which in turn would typically leave a larger residual vacuum energy, not the small one we see. This forces a difficult choice. Either supersymmetry is more subtle and hidden than we thought, or the solution to the vacuum energy problem lies elsewhere, perhaps in a yet more exotic cancellation mechanism, or in a radical rethinking of how gravity couples to the quantum world. The quantum vacuum remains the most glaring paradox at the heart of physics, a cacophony of infinite energy that somehow whispers with just enough force to accelerate the universe. The quantum vacuum's silent scream hints at infinities we cannot hear, but a new kind of cosmic messenger is now carrying a clearer signal through the fabric of spacetime itself. This messenger is the gravitational wave, a ripple in the geometry of the universe, and it offers us a tool of unprecedented purity to measure cosmic expansion. We call these tools standard sirens. The name is a deliberate echo of standard candles like supernova, but with a fundamental difference. A standard candle's distance is inferred from the dimming of its light, which can be obscured by dust or confused by evolution. A standard siren's distance is read directly from the physics of the wave itself. The concept is beautifully simple and rooted in general relativity. When two incredibly dense objects, like neutron stars or black holes, spiral inward and finally merge, they shake the cosmos, sending out gravitational waves in a precise, predictable pattern. The amplitude of those waves, how strong they are when they reach our detectors, tells us exactly how far away the cataclysm occurred. It is a direct geometric measurement, like hearing a siren and knowing from its loudness exactly how distant the source is, without needing to see it through fog. But to use this siren as a cosmic yardstick, we need one more crucial piece of information: the redshift of the host galaxy. That is where the magic of a multi-messenger event comes in. On August 17, 2017, the LIGO and Virgo observatories detected the gravitational waves from a pair of colliding neutron stars, an event dubbed GW 170817. For the first time in history, telescopes across the globe and in space saw the brilliant afterglow of that same collision, a kilonova, pinpointing the host galaxy. That optical counterpart gave astronomers the redshift, the measure of how much the universe has stretched since the merger. In one observation, they had both the distance from the gravitational waves and the recession speed from the light. This single event provided a direct, one-step measurement of the Hubble constant, completely bypassing the entire traditional cosmic distance ladder with its Cepheid stars and supernovae calibrations. The result was a thrilling proof of concept, placing the expansion rate squarely between the values from the early and late universe, though with large uncertainty due to it being a single data point. This is just the beginning. The future of cosmology will be written by these ripples in space-time. As the current generation of detectors like LIGO, Virgo, and CAGRA become more sensitive, they will hear more of these binary neutron star mergers, building a statistical sample that will narrow down the Hubble constant with ever greater precision. But the true revolution will come from space. The Laser Interferometer Space Antenna, or LISA, is a future mission designed to detect gravitational waves at much lower frequencies. While LIGO hears the final, frantic seconds of stellar mass black hole mergers, LISA will listen to the slow, century-long dance of massive black holes in the centers of galaxies, millions of years before they collide. These are supremely loud standard sirens, visible across the entire observable universe. By the time they merge, we will have tracked their orbit with exquisite precision, knowing their intrinsic properties and thus their true distance with minimal uncertainty. LISA will provide a catalog of these events at vast distances, allowing us to map the expansion history of the universe directly and cleanly, from the relatively nearby to the extremely far. This independent, geometric probe could be the final arbiter of the Hubble tension. It will tell us, definitively, whether the discrepancy is a flaw in our local distance measurements, a sign of new physics in the early universe, or something else entirely. In the quiet hum of a laser beam measuring the microscopic stretching of space, we may find the clear, unambiguous voice that resolves the greatest conflict in modern cosmology. Gravitational waves are a pristine new voice in the cosmic choir, but to truly understand the song of dark energy, we need a chorus of billions. This is the monumental task of the next generation of observatories, machines built not just to see the universe, but to measure its every heartbeat with a precision that borders on the unimaginable. Their combined gaze will transform cosmology from a science of hints into a science of definitive answers. Leading this charge from orbit is the European Space Agency's Euclid telescope. Euclid's mission is singular: to map the geometry of the dark universe. It will image over a third of the entire sky in both optical and near-infrared light, measuring the shapes and precise distances of more than 1 billion galaxies. Its primary weapons are weak-gravitational-lensing and baryon-acoustic-oscillations. By charting the subtle distortions in the shapes of these distant galaxies, Euclid will construct the most detailed three-dimensional mass map ever made, tracing the invisible cosmic web of dark matter. Simultaneously, by pinpointing the positions of tens of millions of galaxies, it will measure the baryon-acoustic-oscillation scale across 10 billion years of cosmic history. This dual approach will pin down the equation of state of dark energy and, crucially, test whether that number has changed over time on the ground in Chile, the Vera Sea. Rubin Observatory is undertaking a complementary mission of breathtaking scope. Its legacy survey of space and time will scan the entire southern sky every few nights for a decade, creating a cosmic movie. It will detect and measure tens of billions of galaxies and stars, discovering millions of supernovae. This relentless monitoring will provide an unprecedented census of Type 1, a supernova, building a distance ladder of staggering statistical power to measure the expansion history. Furthermore, Rubin's deep, wide-field images will produce its own exquisitely detailed weak lensing map, offering an independent and cross-checked view of how dark energy has suppressed the growth of structure. Joining this effort from space will be NAS, a Nancy Grace Roman Space Telescope. With a field of view 100 times larger than the Hubble Space Telescope, Roman is a wide-area survey machine. It will conduct its own high-resolution near-infrared surveys, excelling at measuring the distances to galaxies using a technique called slitless spectroscopy. This will provide a galaxy map of exceptional depth and accuracy for baryon-acoustic oscillation studies, and its infrared eyes are perfectly tuned to peer through cosmic dust to find supernova in the early universe, probing the very onset of acceleration. Meanwhile, on the radio wavelengths, an entirely different kind of giant is rising. The Square Kilometre Array, or SKA, will be the world's largest radio telescope, spread across South Africa and Australia. While it will study many mysteries, its contribution to cosmology is profound. By detecting the faint radio emission from neutral hydrogen gas in billions of galaxies across cosmic time, the SKA will map the large-scale structure of the universe in 3 dimensions out to the farthest distances. This hydrogen map provides another, completely independent measurement of the baryon-acoustic-oscillation ruler, free from the optical uncertainties that might affect other surveys. The combined power of these titans is not merely additive, it is transformative. Together, they will deliver percent-level precision on the parameters of dark energy. They will measure the equation of state parameter, W, and its possible evolution, with such certainty that a deviation from the simple cosmological constant value of -1, no matter how tiny, will stand out like a beacon. They will measure the growth of structure so precisely that any suppression or enhancement caused by modified gravity or interacting dark sectors will be laid bare. This is not just about confirming what we think we know, it is about discovering what we have missed. The data may finally resolve the Hubble tension, revealing whether it stems from measurement error or new physics. It could force us to abandon lambda CDM for a more complex model, or it could lock the simple cosmological constant in place as the undeniable, if puzzling, truth. These observatories are our ultimate instruments of interrogation, built to ask the cosmos a direct question and wait, with perfect patience, for the light of billions of galaxies to whisper back the answer. These colossal new telescopes promise answers, but they may first deliver a deeper crisis. For all their power, they are built to test a specific story, the lambda CDM model. This elegant framework, with its cosmological constant and cold dark matter, has been the triumphant standard for 2 decades, fitting a breathtaking array of data. Yet now, under the strain of ever more precise observations, its foundations are groaning. The Hubble tension is not an isolated crack. It is one of several, each a stubborn anomaly that refuses to be smoothed away by minor adjustments. Alongside it sits the cosmological-constant-problem, a theoretical abyss so vast it screams that our physics is incomplete. We have the whispers of the axis of evil in the ancient light, the puzzling strength of the integrated Sachs-Wolf effect, and the persistent feeling that the coincidence of our epoch is too perfect to be an accident. Individually, each could be a statistical fluke or a measurement glitch. Together, they form a pattern, a chorus of dissonance that suggests our beautiful model might be a beautiful approximation, correct in its broad strokes but missing the crucial fine print of reality. We are faced with a haunting question: are we witnessing the slow-motion collapse of a scientific paradigm? History offers a sobering mirror. We have been here before, at the edge of a conceptual cliff. For centuries, the Ptolemaic model of the universe, with Earth at the center and planets moving on complex epicycles, was a masterpiece of empirical science. It predicted planetary positions with remarkable accuracy for its time. But as observations improved, the model required more and more elaborate, ad hoc fixes to account for the discrepancies. The epicycles piled up. The system worked, but it was becoming ungainly, a clear sign that the underlying premise was wrong. Then came Copernicus, who dared to place the sun at the center. The new model was initially less accurate in its predictions, but it was simpler, more elegant. It offered a truer foundation, and once refined by Kepler and Newton, it unlocked the cosmos. Today, lambda CDM feels eerily reminiscent of a pre-Copernican model. It fits the data spectacularly well, but to maintain that fit in the face of new tensions, we are adding conceptual epicycles. Early dark energy, evolving neutrino masses, phantom fields, these are not necessarily wrong, but they are complex additions invoked to save a simple core. The cosmological constant problem itself is the ultimate epicycle, a grotesque fine-tuning that our theory cannot explain, only accept. This accumulation of fixes is a classic symptom of a paradigm under stress. The model is not broken, but it is bleeding, and the bleeding points to a deeper wound. So what might a Copernican revolution for cosmology look like? It would not discard everything we know. Just as Newtonian physics remains valid for everyday life, lambda CDM will likely stand as an excellent approximation for a vast range of cosmic phenomena. But for the deepest questions, the origin and fate of the universe, we may need a new foundation. A true paradigm shift would not just add another field or particle to the dark sector. It would fundamentally rewire our understanding of the ingredients or the laws. One path is a radical reimagining of gravity itself, not as a minor modification, but as an emergent phenomenon. Perhaps gravity is not a fundamental force, but a statistical consequence of the entanglement of quantum bits of information on the cosmological horizon, a direct link to holographic ideas. In such a framework, cosmic acceleration might not be driven by an energy, but might emerge naturally from the way information is encoded and processed on the boundary of the observable universe. Another path is to reconsider the nature of space-time. What if the smooth continuum described by Einstein is an illusion, a macroscopic average of a discrete quantum gravitational foam? In this pixelated reality, the expansion of the universe and its acceleration could be thermodynamic effects, akin to the way gas expands, driven by the statistical behavior of the underlying microscopic degrees of freedom. The cosmological-constant-problem would then be a sign that we are mistakenly applying smooth field concepts to a granular reality. Alternatively, the shift might come from redefining the dark sector not as two separate, mysterious substances, but as a single, complex phase of a unified quantum field that interacts with itself and with ordinary matter in non-trivial ways. This would be far more sophisticated than the simple Chaplygin gas. It could involve fields with non-standard kinetic energy, or interactions that change with the density of the universe, naturally explaining why dark matter seemed to dominate in the past and dark energy takes over now. Most radically, a new paradigm might force us to abandon the notion of a single, objective cosmic history. The quantum nature of the universe might mean that different histories contribute to what we observe, and our smooth expansion story is a classical average of these possibilities. In such a view, the Hubble tension could arise from a mismatch between histories that contributed more to the early universe and those that dominate today. We are at a thrilling, uncertain crossroads. The next decade of data will not just provide better numbers, it will perform a stress test on reality as we conceive it. Either the tensions will resolve within the comfortable, expanded boundaries of lambda CDM, or they will shatter it, forcing us to write a new set of rules for a universe far stranger and far more fascinating than we ever presumed. Our place in this story is not just that of observers, but of fleeting witnesses to a cosmic transition. The profound implications of an accelerating universe reach far beyond equations and data, touching on questions of meaning, destiny, and the very limits of knowledge. If dark energy is a cosmological constant, then the future it writes is one of infinite, lonely expansion. All galaxies beyond our local gravitationally bound group will eventually be pushed beyond an invisible horizon, their light stretched to wavelengths we can no longer detect. The universe will not end in fire or ice, but in a gradual, inexorable fading. The cosmic microwave background will redshift into utter invisibility. Distant galaxies will wink out of sight, not because they die, but because the space between us stretches faster than light can bridge it. Future astronomers in our Milky Way, billions of years from now, will look up and see only the stars of their own island galaxy, adrift in a black, seemingly static void. All evidence of the Big Bang, of an expanding cosmos, of other island universes, will have vanished from their sky. The entire epic history of the universe will become unknowable, erased by the accelerating expansion itself. We live in a uniquely privileged moment, a sliver of cosmic time where the past is still visible in the ancient light, and the future's outline can still be deduced. We are positioned at the last cosmic crossroads where the full story is still legible. This leads to a haunting philosophical question: is the mystery of dark energy a puzzle we are meant to solve, or is it a permanent veil? The acceleration may be more than a physical phenomenon. It could be a cosmological limit on knowledge. Consider the horizon created by this expansion. There are regions of the universe whose light, emitted today, will never reach us because the space between is stretching too fast. Those regions are forever beyond our causal reach, their events and physics permanently hidden. What if the ultimate theory of everything, the final answer to why the universe is the way it is, requires information from beyond that horizon? We could be like a scientist trying to understand an ocean by only ever examining a single, isolated droplet. The full truth may be distributed across a cosmos that is actively hiding most of itself from our view. The acceleration, then, might not just be a feature of our universe, but a fundamental constraint on any civilization that arises within it. We may be constitutionally barred from attaining a complete understanding, forever pondering a mystery whose solution lies perpetually over the horizon. This casts our current struggle in a new light. The Hubble-tension, the cosmological-constant-problem, the whispers of anomalies, these are not just technical challenges. They are the edges of our cosmic prison, the walls of the observable cell we inhabit. Our drive to solve them is the ultimate expression of curiosity, an attempt to read the entire story from a single, fading page. Whether we succeed or not may define the difference between a universe that is ultimately knowable and one that is designed, or has evolved, to keep its deepest secrets forever out of reach. The accelerating expansion forces a humbling choice upon us. We can see it as a countdown clock, granting us a limited time to decipher the cosmos before the evidence disappears. Or we can see it as a fundamental lesson in cosmic humility, a reminder that some truths might belong to the universe alone, and not to the temporary minds that briefly flicker within it. Our greatest legacy may not be in finding the final answer, but in the profound questions we dared to ask during our brief moment in the sun, before the long night of isolation falls. Our journey has taken us from a single, shocking discovery to a universe woven with 30 distinct threads of mystery. We began with the Hubble-tension, a concrete conflict in the numbers that measure our cosmos, and spiraled outward into the profound enigma of the quantum vacuum. We have encountered phantom energies that could rip reality apart, and holographic principles that suggest our world is a grand projection. We have weighed the possibility that dark energy whispered in the infant universe, and considered the chilling thought that we live inside a cosmic illusion, a statistical fluke in an infinite multiverse. Each proposed answer, from modified gravity to unified dark fluids, solves one piece of the puzzle only to create new, deeper questions elsewhere. This is the defining signature of a living science. Cosmic acceleration is not a closed chapter in a textbook. It is a sprawling, active frontier, perhaps the greatest in all of modern physics. The telescopes now scanning the sky and the theories being scribbled on blackboards worldwide are not merely refining a known truth, they are hunting for an unknown one. The next great leap in understanding might arrive with a single, anomalous data point from a new supernova survey. It could emerge from a stroke of mathematical genius, connecting string theory to the cosmos we see. Or that spark of insight might come from you, from a mind ignited by curiosity, looking up at the night sky and wondering what strange force is at work in the darkness. The story of the accelerating universe is still being written, and its next author has not yet been chosen. Stay curious, keep looking up. The greatest mystery is still out there, waiting.